Okay. All right. So this session is to make up for the January 21st session that we were out for snow days. Hold on, I still got people coming in. Okay. And so you'll either need to attend like you are, or watch the video afterwards. But to account for your attendance, I need everyone to take note of these three keywords that I'm going to give out throughout the session. And then you'll go in afterwards to this virtual assignment. I'll show you a preview of it. And it will ask you what the three keywords are. You'll type those in and then indicate whether you attended the live session or you watched the recording, and then submit the quiz. And this will be used to kind of account for your attendance for the for this day. So I've added that in there, and there's some other information here in this. I just named it SB2 so that we didn't get out of, they could still be ordered correctly. But the virtual session here, there's information about that, but here's additional information for those keywords. So whether or not you attend live or watch the recording, you'll need to type in those three words after the session. I did put that till March 17th. Most of you can go in there and do it right after this. That's perfectly fine too. But just in case, you have till the 17th to do it. For the agenda for today, we're going to go over some of the formulas and concepts. We do have a test coming up in week 9. So when you guys get back, you'll have kind of another week to study, if you will. And then on the 24th will be the test will be due, and it will be on the lensometer. So you'll have another time in class to work on the lensometer, practice with that a little bit more. And we're also going to go over some of that today as well too. But we'll go over some of the formula and concepts, the oblique meridian, Prentice Rule and base direction. We'll look at transposition practice again, the optical cross, index of refraction, some points about the boxing system, and some clarification on the Abbe value and what that is and why do we care. Also the lensometry, power drum readings. We'll look at, if we have some time, I want to look at a couple of different things about the lensometer that might help make this a little bit more, make more sense. And then we'll review some of the ANSI application, some of the main points from that. If we have time, I was wanting to also maybe talk about the worksheet that was due Monday, yesterday. Any questions about that? Because that'll be on the test as well too. So when I'm done recording the session, I have to kind of make a couple little edits and download it and then upload it here. But it'll be up here no later than Wednesday, tomorrow morning, for later review or whatnot. So let's go ahead and get started. Another thing in this module here, I've also put some extra credit assignments for the theory worksheet and the power drum reading worksheet. That was a little bit, if you had problems with that. So the extra credit, there's information about that here in this one and a link to both of those. One of them was available and the other one was not, so they are available now. So if you're on your computer and you want to open them up and start to kind of look at them, but the theory of light, the theory worksheet, I really recommend if you scored below 80 on either the worksheet 2.2, the theory review, or on the test, that you can complete this worksheet to make up some of those points for those concepts that you missed. And then for the worksheet 5.3, the lensometry introduction, specifically that power drum reading section, complete that. Everybody is able to see the screen, correct? I should have asked that a little bit earlier.
Yes, I can see.
Okay. Okay. All right. Thank you. Um, Regardless of your score, if you want some just extra practice, you can absolutely do this for some extra credit. You know, if you got outstanding results on certain stuff, we might have to find the extra credit fits somewhere else. But it's regardless, this is really good practice with these formulas as you guys are preparing for that ABO basic exam that you'll be taking. You know, a lot of the little basics here are really important to understand before and while you're taking that exam. These are both due. I put them out till the 23rd. I just put them out for the 23rd. Ideally, I'd like you to definitely do these before you take test one or as soon as possible. I'm not sure what your other classes look like, content that you've got to work on over the spring break, but this would be ideal to work on these during that break, and then you'll just submit them like you do projects. But regardless, they're open until the 23rd for you to submit for the extra credit. So they are in the modules here. This is these two. You can access them. They're also right here. Same content, but when you guys go in, you'll be able to download the worksheet. I put it on here. So it'll look like this. This is this first one, the extra credit for the theory and the formulas. And it kind of gives you just a little, you know, why do we care about this and what is this formula and what does it do? So make sure you definitely take some time to read through this. But it gives you some questions that you can practice using the oblique meridian formula to figure out that power at 90 and the power at 180. Remember, we're always concerned with those because the vertical is the OC that we deal with, the optical center height. And the horizontal is with the 180 because we're dealing with PD, pupillary distance of the person. Then we've got Prentice Rule on here, and it kind of goes through. These were the same 8 types of questions. If you'll notice, I took questions directly from the test so that it wasn't just as cut and dry as here's the prescription, here's how far they're looking away. It's more like, you know, what's the prism effect? So we'll kind of look into these a little bit today and talk about those in more depth, but this is just kind of going over what's on this worksheet. So and then there's some prism based directions. So we'll look at looking at that kind of thing and how to figure out, draw that out. There's some practice on transposition and making sure whether you're being asked whether we want it to be in the plus or the minus cylinder form using the cues here. A little different questions about the optical cross. So just thinking about that and getting that really solidified in your mind. These are, again, kind of the questions right off the test that, of course, the numbers have been changed, but so that you see them how you saw them that day. So we'll talk a little bit more about that and the nominal power formula. Again, what are you being asked for in these first 3? We're asked about the back curve, and the last 2 were switching it up and asking about the front curve, and then also the lens power itself. So depending on what variable, what 2 variables you're given, you can of course solve for that missing one. Look at the speed of light formula again, just kind of go through that one, and just, you know, we'll talk about that. And then also the boxing system here, being able to label this whole diagram without looking up anything, and knowing a couple little bit of points about it. That's what these are down here. Definitely a good thing to be able to do. And then I put some clarification information too about the Abbe value. There was a couple questions on the test that were kind of asking about, you know, you were told that higher Abbe value. You were told, you were asked about a lens with a higher Abbe value versus a lower Abbe value, and those are right in here. So we'll talk a little bit about this as well. But in the end, I just kind of at this point want you to understand the concept of, what does it mean when the lens has a higher Abbe value versus a lower Abbe? Because it is kind of backwards. Most of the time, you'd think a higher Abbe value means more, a bigger problem, but it's actually the opposite. The higher the Abbe value, the less distortion or aberration that we get from that versus polycarbonate down here at the lower end of the Abbe at 30. So that is a lower Abbe, which has more noticeable aberrations, chromatic aberrations. So that one is the formula and theory one. And then there's the other one, which is your power drum worksheet. I made this a little bit more hopefully helpful, but you basically see your first reading here, and this is saying that when the sphere lines, so this is an example of what it might look like. You see the 3 thin lines. Then you get your second power drum reading, and that's when the cylinder lines are focused and the axis is rotated to, on this one is 0, but remember we write that at 180. And then basically taking these 2 power readings and that axis and writing out a prescription for it. So we'll talk about that and then transposing it. And so that's what you're doing on this worksheet. And so the questions themselves are pretty straightforward, but I want you to kind of keep in mind all of this is going on behind the scene. And you could do that with each one of these. For this first one, first reading is 7. We just imagine that this is 7. This whole scenario is happening. And then when we read that second reading, this is when the cylinder lines, and so this scenario is happening. And then the axis wheel is rotated to 12, and so this is happening. And then these all will be kind of the same thing. So there's 10 of those on here. Those were worth like 4 points on the worksheet. And so if you made any mistakes on that one, it was hitting the points pretty hard. So hopefully this worksheet will help you get clarification on it and also help to boost up your score a little bit. So I don't want to get ahead of myself. Back here. So again, this is all in that spring break module. Yeah, none of this other stuff was here until recently. These are optional assignments. You do not have to do them. If you feel comfortable with all those concepts and you don't really want to do it, you don't have to, but I strongly suggest anybody who struggled with any of those or got scores that they weren't 100% happy with, or if you just want the extra practice to complete those. Let's look at the oblique meridian formula. The oblique meridian formula is calculating the power in a specific meridian of the lens. This is only used for lenses that have cylinder power. So lenses that have prescriptions that look like this. We got the extra number here. These numbers right here let us know that we're working with a cylinder power lens. And so this formula allows us to kind of calculate that exactly. So that allows us to calculate the exact power of the lens, right? And we're going to figure out what the power of the lens is at 90 and 180. And we're just going to use straight in the calculator. So for this one that's at 90, we want to take the axis that we want minus the axis that we have. So 90, and make sure you're putting this in your calculator. I'm going to do it on mine too. So we take the 90 minus the 20, enter, and you get 70. If you put it in the opposite way, it won't matter. 20 minus 90 is going to be minus 7 or negative 70. That won't matter. Then you take this and you're going to sign it in the calculator. So hit your sign button, and you should get 0939 and some change. Then you're going to square it. Square it. You should get 0.883. Multiply it by the cylinder amount, and the cylinder amount is -2. and then add it to the sphere, which is -3. And I got 123.39, which we're going to just truncate that, because the powers will be in 2 decimal places after. So we're going to truncate that 39 right off. And so -123. Did anybody else get anything different?
I got a -4.766.
Yeah, you're probably right, because I'm looking at my powers here, and with those powers, the 2 major meridians, I can't possibly have what I got. 766. Okay, so we could either just truncate that 6, round it to 4.77, or just include it. The one thing you wouldn't want to do is round any of these powers to dioptric increments. Whenever we're dealing with that oblique meridian power formula, we really want to know what the power is in a particular meridian. So we would either want to work with this as a -476 or -477. We wouldn't want to make it pretty and put it at -475. That'd be rounding too much. All right, so the same thing when we're going to do the power at the 180, we just say what's 180 minus the axis that we have, and then we repeat this process. So plug this one into your calculators too. So I've got the axis that I want is 180 minus what I've got in the prescription, which is 20. That gives me 160. And then I assign that value. So I hit the sign key and enter. And then I square that value. So I assign, and then I'm going to square the value. Square it, enter. And then that leaves me, what this leaves me with is a percentage, and that's when I'm going to multiply it by the cylinder amount, which is -2. So multiplied by 2, negative. You want to make sure you keep up with your signs. And I get another value. That's the percentage, or power, I should say, the power of my cylinder now that is in effect. And I'm going to add that to my sphere power, which is -3. And I got -3.2339, something like that.
Yes, that's what I got.
All right. Okay. All right. So does everybody feel pretty good? These are, kind of just getting comfortable with your calculator, making sure you can do the sine and the square, and making sure you keep up with your power signs, because that'll make a big difference in your end result. Have y'all talked in dispensing about the 30, 45, 60 rule to figure out the power? That is another technique, or when you're doing your ABO exam, you're going to notice that the axis is for the prescriptions are generally those either 30 or 45 or 60 or 90, 120, 135, 150, or 180. And those axes are specific. Okay, so because they equal a certain percent. Let's look at an example. Plano -1 at axis 90. Okay, when we look at this prescription, there's a couple of things. If I asked you what's the power at 90, okay, what's in the vertical meridian, and then what's the power at 180, what's in the horizontal meridian, looking at this prescription, I hope you can quickly see that, well, the 90 is the axis that we've got, and that's always associated with that sphere power. So really quickly, I can know that I have no power in this 90 meridian. And 180 degrees away, that's this right here, at 180, I have this full amount of cylinder in effect, right?
Yes.
And so the total power that I have here at 180 is the -1 cylinder, because that is 90 degrees away, and it's 100% of the cylinder is in effect 90 degrees away from the axis. All right. Well, if I have the same thing, but my axis is now 30, then the question becomes, well, at 90, what power do I have? And at 180, what power do I have? 90 and 180 are like this, right? So these are my 90 and 180, but my prescription or my lens is at 30, which comes about right here. And then this one's 90 degrees away, so that should end up being at 120, right? So this is 30 and 120. Am I right? 120 and 30. And so this axis, if we, at 30, we have plano here. So we have 0 power here at 30. And then 90 degrees away, we have the full amount of cylinder power. Then 30
By force.
from this 180 is exactly 30 degrees, and up to the 90 is exactly 60 degrees. Okay, so how that breaks down is 0 degrees away from the axis equals 0% of the cylinder, meaning this 90, 0 degrees away from 90, or at 90 we have plano. And then we've got 30 degrees, 45 degrees, 60 degrees, and 100 degrees. And all of these equal a certain percentage of the sill. And these degrees that we're talking about are right here. So we're 30 degrees away from 180 here. 30 degrees is 25% of the sill. 45 degrees is 50% of the sill. 60 degrees is 75% of the sill. And 90 degrees is 100% of the sill. So when you're looking at this one, if the axis for this one, we have plano power of at 30, and we are how far away from we're going to do the 90 power. How far are we away from the 90? We are 60 degrees away from 90, right? Because this is where my 30 is, and we are 60 degrees away from 90 here. So 60 degrees away from 90, right, is this one. And so that is 75% of the sill. The sill value is that -1. So 75% of that -1 would be -75. And we don't have any power in the sphere meridian. So the power is exactly 70 minus 75, which is 75% of the sill. When we look at the 180, okay, so from 30 to 180, that would be
minus 0.25.
Yeah, that would be this 30. So 30 degrees away from 180 would be 25% of the sill, this one right here. And so we would have a quarter, because 25% of this -1 here is a quarter. And again, we don't have any power in the spherical meridian. So we only, the actual power ends up being minus a quarter in the 180. And that changes a little bit when, well, not changes, but it adds another layer when we introduce a sphero cylinder amount. So let's do 60. So, so 60 comes about right here, and 90 degrees away from that. It's about right here. All right, so at 60, we have -2. And 90 degrees away from that, we have -3. Because remember, the -2 is the sphere power, and it's all over the lens. And then we have another -1 that we're adding when we move from here. So that's how we got that. And then this is the 60, and this one is 90 degrees away from that, so that should put us at 150.
Roughly.
All right, so looking at our chart back up here again, how far are we? So there's our -2, here's our 60. How far are we away from 90 on this one? And you could just say 90 minus 60, and you're going to see that it's 30 degrees. And this 30 degrees is going to be used here, which is a quarter or 25% of the sill. So 25% of this -1 is -25. We're 30 degrees away from 90, and that equals 25% of the sill. And when we did that, we found out that we had -1/4 is the amount of the cylinder that we have in effect. And then we just add that to our sphere value that we have, which was -2. And that's going to give us a -225. So at 90, we have -225. And then if we want to also know what the amount was here at 180, what the power is at 180, how far are we away from 180? So you could do the same thing where you subtract, 60 degrees. Or for the 180, it's best to think of it as this 0 if you're over in this first quadrant here. If you're over here, think of the 180 as 0. And then if you're over in this area, you'll want to think of the 180 as the 180, just because the way the math works out better for you. So you're 60 degrees away from the 0 or 180. So, and 60 degrees was 75% of the sill. So 75% of that is -75. So yeah, 75% of this is 1 is going to equal -75, and then we're going to add that into our sphere, which was -2. And that's going to mean we have 275 at our 180. Probably the easiest one to memorize first is whenever you have an axis at 45 or 135. So let's do 45 for the axis here. And so quickly, without even thinking much about it, you should be able to be like, oh, okay, well, at 90, I'm going to have, it's 50% of that cylinder. So basically, it's my spherical equivalent. So at 90, I'm going to have -250. And at 180, I'm also going to have a -250. And the reason this is true is because... And so a 45-degree axis looks like this. Here's our 90 and 180 again. And 45 degrees cuts exactly in halfway. So it looks more like this. And then from the axis that we're at to the one that we want, these are both exactly 45 degrees away from each other. And those are 50% of the cylinder is in effect. So that's 50%. And so if I write this or label this one up at 45, I've got -2. So I got -2 here at 45 and -3 here at 135. Yeah, 45 degrees away from this 90 and 180. I'm exactly halfway. So the powers that I have in this lens at 90 and 180 are the exact same. So anytime you get one of those 45-degree angles or 135, 30 here, 45, 60, and then we kind of duplicate that over on the other side with 125, 135, and 150. So what's happening over here is just kind of duplicated on this other side of it. So you kind of think of their kind of mirror image, if you will. 30-degree axis, and then its counterpart would be 120, and 45 degrees would have 135 would be its counterpart, and 60 degrees is 150 is its counterpart. We would have 0 and 90, but again, remember 0 is 180. But yeah, anytime you see that axis 90, 180, you can do like the shorthand version. And then if you see an axis that is 30 or 125, you can do, or 120, you can do the shorthand, because the amounts away are always going to be in this kind of 30, 45, 60, or 90 degree amount away from the meridian in question. All right, so let's do a practice one, or what's the power of this lens at 90 and 180?
Minus is 3.5.
-350, and that's in both of the meridians, isn't it? And so we didn't need to necessarily, for this one, we didn't need to calculate what the, or calculate necessarily what it was, because it's got one of those kind of magic axes. So 135, remember, is halfway, boom and boom. So from the 90 and the 180, and this is on both sides of it, from the 90 and the 180, we're exactly 50% of the way there. So we take 50% of the cylinder. We took 50% of this, and then we added it into that -3. And so 50% of that seal was -50, and we added it into the -3. What about with this one? +2 at 45. That's another one that's 50%. So looking at it real quickly, you can say, okay, well, 50% to get to 90 and then the 180. So to get to the 90 from here, I'm 45 degrees away, which is 50% of this seal. So 50% of this 2 is +1, correct? And then we add that into our sphere value. So did everybody get +6?
Yes.
All right. Okay. So this, again, these are our 50% ones. So what if I've got +2, +3, an axis 30. All right. Now the question is, what's my power at 90 and what's my power at 180? All right, well, looking at that axis, we got a 30-degree axis. How far are we away from 90? 60 degrees, right? Yeah, 60 degrees. So 60 degrees is what's the percentage for 60 degrees away? How much of the sill's in effect?
0.75.
So 75%, yes. So 75% here, okay? So 75% of the plus 3. If you're doing this in your calculator, you just take that 3 and you multiply it by 0.75, and that will tell you your amount. Make sure that you keep up with your signs on this. When you multiply that, did you guys get plus 225? That's how much of the cylinder is in effect. And then we just add that to the sphere power. And so at 90, did you guys get 425 for the power at 90?
Yes. Yes.
All right. Now the other question is, what is the power at 180? And so now for this one, we're going to have a different percentage because 30 is how far away from 180, remembering that the 180 line is also equal to 0. So we are exactly 30 degrees.
30 degrees. 25%.
Okay, good. So 30 degrees away from the 90 is 25%. So 25% of the 3 is going to be, oh, I lost my calculator. So if you're doing this in your calculator, you say 3 times 0.25, and y'all should get plus 75. And then we'll take
275.
that.
Yeah.
All right,
Sorry.
and then we'll take that and we'll add that into our 2. So we get plus 275 for the power at
Yes.
180.
Yes.
Yes.
All right, let's do another one. Let's do minus 4 plus 4. All right, at axis of 120. All right, and we want to know what is it at 90 and what is it at 180. So for 90, the 120 is how far away from 90?
30.
30 degrees. So if we're 30 degrees, 30 degrees equals 25%, right?
Mhm.
So 25% of the 4. So in your calculator, 4 times 0.25. And did you guys get plus 1?
3.
Is that right?
Yes.
Yep. Okay, yeah, because we're 30 degrees away from 90. That's how we figured out our degrees amount. And then we know that 30 is 25% of the sill. So we took 25% of the 4 and we come up with plus 1. And then we add that plus 1 into our sphere of minus 3. Think money. And we come up with
Minus 3.
minus 3. Very good. All right, and now let's do it for the 180. I'm going to take these back out. So for the 180, how far is the 120 away from 180? 60 degrees, and 60 degrees is 75%, right? So take that 75% of plus 4, and we have plus 3.
3.
All right.
Mhm.
So plus 3, and then we add that into our minus 4. And so we come up with
Minus 1.
Yep. -1.
minus 1. Let's do one more. Let's go 5 minus 150 at 150. All right. And then we want to know what power at 90 and what's the power at 180. So looking at this, how far is 90 from 150? Is that 60? 60 degrees is 75%. So 75% of the 150, 0.75 times 150 negative gives me a minus 1,125. Is that what you guys get?
Yes. Minus 6.
And then we add that into there, and we come up with minus 6,125.
Yes.
Yep, good. All right, and then for 180, how far are we away from 180? We're 30 degrees, right? 30 degrees is 25%, so 25% of that 150 minus 375. And then we add that into our sphere value, and we come up with minus 375. Basically, what we're doing with Prentice Rule is we're trying to figure out how much prismatic effect is caused when the wearer looks at a point that's not the optical center. So you need to keep up with where the optical center is and where the point that they're looking. So some of the things you need to know is what meridian is in question and what the power of that lens is, because with Prentice Rule, we know that we've got the prism amount, we've got the dioptric power times the distance in millimeters divided by 10. So that's our formula. And when it comes to that dioptric power, we can only use one number in there. So that's why we often need to use that oblique meridian formula, or the rules that we just used or covered, that 30, 60, 90, 30, 45, 60 rule, to figure out what the power is at a given meridian. And then we can use Prentice Rule. Right here, we can use Prentice Rule to determine the prism effect, and then we can look at where the eye is in relation to the optical center and determine what the base direction is. So this was one of the questions that came right off the test, looking at question number 1 right here. What prismatic effect would be experienced by the wearer if the OC is accidentally placed 5 millimeters higher than requested on this lens that's a single vision? So here's our prescription. Here's how far off from the OC that the wearer is going to be looking through. And so we can tell right now we need to use Prentice Rule. We can tell from this that we're going to need to use the oblique meridian formula to get that into one power. So what is the meridian in question, and how do we figure out what meridian that is? Well, based off of where that optical center is versus where the person's eye is. We know the amount is 5 millimeters, but higher than requested is what we're looking for. So higher than requested, we can actually start to, anyway, it was higher than requested. So we're dealing with kind of an up and down because we're dealing with higher. So that would be up and down. And so the meridian in question for this one would be the 90th meridian. And what is the power that we get in the 90? Let's look at it. How far is this axis away from 90? We're 60 degrees, correct?
Yes.
So we're 60 degrees away from 90. So that gives us 60 degrees equals 75% of the sill. So we're going to take 75% of the cylinder mount, which would be plus 75, and we're going to add that into that sphere value that we have. And that's negative sphere value. So we're going to add that into our sphere value, and we come up with minus 325. Is that what you guys come up with?
Yes.
So the power that
Yes.
we're working with here at 90 is minus 325. And now we can calculate what our prismatic effect is using Prentice Rule and that 5 millimeters and this as our dioptric power. So remember, Prentice Rule, big D times little d divided by 10. So we'll plug those in, and we've got minus 325. That's the power, times the 5 millimeters error divided by 10 is going to give me, so 325 times 5 divided by 10. Did you guys get 1.625? Something like
Yes.
that? Good. So 1.625, this is a whole lot of extra, so we'll just put this down to 1.6 diopters of prism. So the prismatic effect here is 1.6 diopters of prism. That is that's a chunky amount of prism. So this person's probably going to feel this. So now let's figure out what the base direction is. So looking back at what we've got, what we're told here in the question, that the optical center is accidentally placed 5 millimeters higher than requested. All right, then requested. This requested is where we'll say the eye is going to be looking, and it's the OC is what was placed 5 millimeters higher. So let's start by drawing this out. We're in the up and down in the 90 here. So we're going to take a minus lens because we're dealing with the 90 and the lens is minus. Okay, so we'll start out by drawing a basic minus lens in the 90 because it's up and down and in the 90. And then we've got, where is our optical center? So our optical center is right here. So put a dot right there. And then where is our eye at? Look back at the question. The OC is accidentally placed 5 millimeters higher. So the OC is higher, 5 millimeters higher than what the eye is at. So the eye is looking through face down prism. So that means that if this pair is dispensed and the wearer is looking through 5 millimeters, is looking 5 millimeters basically below the optical center, or if the optical center is placed 5 millimeters too high, then this person will experience 1.6 diopters of base down prism in that eye. All right, and so let's do another one here. Let's do this one. So prismatic effect, looking through 6 millimeters nasal to the optical center. Okay, so here is our little d, there's our big D, and you were trying to figure out what the prismatic effect is. So what meridian are we dealing with in this question? And so what power of the lens do we need? Well, where's our error? Our error is right here. So we're 6 millimeters nasal. The eye is basically looking through a point that's 6 millimeters nasal to the optical center. So nasal's the key word. So that means we need power exactly in the horizontal. So what's the power at 180? This prescription is at 135. And remember, that's that 50%. We're halfway between the 90 and the 180. So we can figure out how far are we away from the 180. At 135, this should be 45 degrees, which is that 50% of the seal. Let me write this different. 50% of the seal. So we're going to take 50% or half of this seal, which is -2, so -1, and add that into the, this is actually a -3, that 3 minus is over there. So we're going to take -1 and add it into the -3, and so we get -4 at 180. Is that what you guys get?
Yes.
Okay. And then we'll take and do the prism effect using that 6 millimeters and this 4. So the dioptric power times the millimeter error divided by 10. So 4 times, so 2?
Yeah, negative 2.4.
2.4.
2.4. Oh, okay. This is 24. Okay. 2.4 diopters. That's our prismatic effect. So we've got 2.4 diopters of prism that they will experience if they are, when the eye is looking through a point 6 millimeters nasal to the optical center. So that's what we're going to use to try to figure out our base direction. You were told what eye, but in the end it wouldn't matter one way or the other. So here is our lens. We drew it in the 180. It's a minus powered lens. We drew it in the 180. Here's our optical center. In order to know nasal or whatnot, we need to put a nose in here. All right, so this is the right eye, and that's the nose. And the eye is looking through a 0.6 millimeters nasal to the optical center. So if they're looking through a 0.6 millimeters nasal to the optical center, are they looking in here or are they looking in here?
The first one.
The first one,
one.
very good. Yes, because the eye is located 6 millimeters nasal. So their eye is actually looking through here. And when that happens, they're going to experience
Face out.
base in.
Face in.
Because the eye is looking through a 0.6 millimeters nasal to the optical center of a minus lens. So this is our so our nose is right here, and they're looking nasal to the optical center, and the base direction of that prism will be base in.
Okay.
So this is base in and base in. And if this was both the right and the left, we would do the same thing here. We would just draw our minus lens. We would mark where the optical center is. And then we would say the person is looking 6 millimeters nasal to the optical center. So that would be this again over here. And we see the base direction of the prism again would be base in. So that's just to illustrate that even if it was the right or the left, when they use words like nasal to and things like that, that will, there's only one direction for the nasal, no matter whether it's technically right or left. Once you know where that nasal is, you can, nasal or temporal. This would be our temporal areas out here. So if it had said, instead of nasal, it said temporal, then you would be moving out towards this section of the lens out here towards the temporal, and then that would have been base out prism because the OC would have been located in on this minus lens. But it doesn't ask you for temporal, so you don't need to worry with that. Okay, and so there's only 2 more questions, and again, if you look at them, technically you can get away with using some of your shortcuts with these, or you can double check yourself using your oblique meridian formulas as well. All right, so looking at base direction, we kind of talked about this again, but there's 3 things you need to make sure that you do, that you know. These are the 3 things you need to know. Whether the power in the lens, what the power is in the prism meridian, whether it's plus or minus, and what the location of the optical center is, and then what the location of the eye is. This will work all the time, no matter whether the person looks away or the optical center is moved away from their eye. There's just basically 2 times that this happens. When we're checking a pair of glasses that they have that we've gotten, and there is a difference between what's the measurements that are in the glasses, so where these will actually sit in the frame versus what the patient's measurements are. So meaning there's some sort of an error in the PD or an error in the height of the lens. And so we need to know, well, if they put that pair on, what will they experience prism wise? Their eyes are going to stay in the same place and the glasses are going to stay in the same place. So you just really need to just examine where the optical center is versus where does the eye end up looking through to determine that prism. The other one, and I think that's what a lot of y'all in theory 2 are learning about right now, is one where the person looks away from the center, namely to read. When they look down to read in the glasses, this is kind of the first time we're telling them you have to look away from the optical center. And that's not a problem so much when somebody has a prescription that's relatively the same in the right and the left eye. It becomes a greater problem when the prescription between those two eyes differs by a certain, once you get to so much amount, then when they look down, those prism amounts are going to be very different. And that's going to cause some, or could cause some amount of an imbalance. So these are the two different reasons that we're looking at these. So for these particular questions, I tell you what the lens is, all of these, minus, minus, or plus. And then I tell you what happens in the glasses. The wearer looks down to read, or the OC is misplaced. The OC is too high. Again, misplaced. Wearer looks down to read. OC is misplaced nasally. The OC is placed too high. So kind of like that. And it might not be as straightforward as that using these exact terms, but that's what you're trying to figure out is where is the optical center in this pair of glasses and where is my person's eye? That doesn't change no matter what's happening. Okay? So looking at this one, I do ask that you draw the two lenses as a prism, mark the optical center with a dot, mark the prism reference point with an X, or the location of the eye with an X, and then answer the question. So looking at this first one, minus lens looks down to read, all right? And they are looking down to read. So minus lens, what meridian am I in? They're looking down. So I'm in the vertical, very good, vertical. So, and it's a minus lens, so I'm going to draw my lens looking like this. And then you want to mark the optical center with a dot. So where is our optical center here? Our optical center is right where those two apex to apex go. And what happens when the wearer looks down to read? So looking at this one, if their eye is normally positioned here at the optical center, right? So they're normally right here looking through the optical center. They don't have any prism. But what happens when they look down to read? All of a sudden now they're looking through.
Down.
Yes, they're looking through this point. And again, the only one that we care about is going to be this one because this is where the eyeball is. And so they are looking through base down prism. So base down, very good. So the question asks you, what base direction is the resulting prism? Base down. And remember that I'm also looking for the picture here, and I'm looking for you to state the amount. So if you just have a little drawing like this, that will work perfectly fine for me. So let's do a couple. I don't want to end up doing all of those on your worksheet. So let's do a couple. Let's say I have a minus lens again, and we're going to say where looks up, or we'll say where looks above OC. What kind of prism is this going to be experiencing? So first off, draw your lens. We're dealing with a minus lens. We're looking above the OC, so meridian.
90.
Yep, 90. So minus lens here. Optical center is here. Where's eye is where? Where looks above the OC? Where's looking up here? What base direction?
Base up.
Base up.
Base up.
Oops, sorry. All right. Let's say they got a plus lens, and OC is 5 millimeters too far out. That's a little bit of a difference. 5 millimeters too far out. Okay, so what meridian are we looking at for this one?
Horizontal 180.
And the 180, we got a plus lens, so let's start drawing that. All right. Where's my optical center? Optical center is at the middle of those. And then we need a nose, right? Or we can draw both of them. So we could draw both lenses here if we wanted to. And then we basically simulate a nose here in the middle. All right. And if the optical centers is too far out. 5 millimeters too far out. Is the eye looking through here or here?
Yin.
1 or
Temporal.
2?
Temporal out.
The eye is going to be looking through here?
No, no, the eye is yin.
Yes.
Close the nose.
I was gonna say,
Yeah.
shouldn't the eye be in the middle and the OC be on the outer side?
OC
Yes,
is
because the OC, yes, that whoever's OC is too far out.
So it's
So
temporal.
yeah, so
the
they're
eye.
actually looking through a point that's nasal because it's saying that it's too far out.
Jason, yep.
So they're actually going to be sorry, I keep hitting that. They're actually going to be looking through a point here. That's where their eyes will. So they would experience base out in each lens because the OCs are too far out. This would be the equivalent of, let's see, a patient's eyes, their PD is actually 60 millimeters. But the glasses, when we check those, the optical center of the lenses is actually at 70 millimeters. So compared to where we need to be from where we are, we're 10 millimeters off. Does that make sense? That the OC PD, if you will, is at 70 versus the patient's PD, which is at 60. Because these are too far out.
So I have a question
Yeah.
for like number 2 on the worksheet where it says the
Mhm.
minus lens OC is misplaced temporarily. I don't know if I said that right. That would be base out.
Correct. Because we're dealing with a plus lens and it's too far
Oh,
out. You could also say this could be, say, too far temporally. That means the exact same thing as too far out. Or it could say too wide, that the OC is too wide, too far out, too much temporally, and so that the patient is looking through a point nasal to that.
So in a minus lens, would that be base out?
This exact scenario for a minus lens would be base in.
Base in.
Let's do that one. So if we had this same scenario of a minus and the OC is 5 millimeters too far out. All right. So we have a minus lens. So we draw our minus lens schematic. And our OC is here at the center. Here's our nose. And then the OCs are too far out. So again, we would have this being like something like 70, but our patient is more nasal. And so they're going to look through here. And so they would experience, in this exact same situation, they would actually experience base in because of the shape of their lens.
Okay.
Let's say we have a plus lens and they're looking 10 millimeters down to read. All right, so what prism effect do we have here? So they're looking down to read, so we're dealing with the
Vertical
90, right? And we've got a plus lens, so we're dealing with a plus. So let's draw our plus lens vertically. Here our optical center, where's that at? It's right there always. And what is the person doing? They are looking down to read. So they look down here. And when they look down there, what prismatic effect does the eye have when it's looking through there?
Base up.
Base up. Exactly. What if I had the same exact scenario, but it was a minus lens and we have the same scenario? So again, we're still in the dealing with the 90. My optical center's right here. And what happens when they look 5 millimeters or 10 millimeters down? They're going to experience
Base down.
Base down. Exactly. All right. Um, let's say we have, let's go plus again, and the OC is misplaced nasally. All right. What do we think that means? Misplaced nasally.
Horizontal 180.
All right. So the nasal lets us know that we're, dealing with the 180. We got a plus lens. So let's start sketching that out. Okay. Here's my nose. We can do a second lens if we want. All right. Where's my optical centers are right here and right here. And then we come back. OC is misplaced nasally. So what do we think that means? The OC is misplaced nasally.
Closer to the nose.
Closer to the nose. Very good. So closer to the nose. And if the OC is closer to the nose, what does that mean for the eye? Where does the eye end up?
Looking base in.
Out here, right?
Yes.
So then they would look, yeah, I think that was Denise. Was that Denise? Yeah, so base in. Does everybody see that?
Yeah.
So there's
Yes.
base. All right. And what if this exact same scenario was for a minus lens? In this same scenario, we're going to draw our minus lens again. Minus lens again. Nose. Optical centers. Boop. Boop. And then the OC is misplaced nasally, so the OCs are too close to the nose, and that results in the eyes being out here, and they will experience base out prism. Let's do one. I want you guys to work on this one. +5 -2 at axis 60. And let's say this person, or let's say the OC is too far temporally, aka too wide, PD, too wide. All right. What I want to know is what would the resulting prismatic effect be for this? And we're going to say that this is OU. So each eye is going to have where the OCs are too far temporally or the PDs are too wide. That's another way to think about that one. So what meridian are we working with is your first question, and what the power at that meridian. Then the second question is how much prism is resulting here. And then the last question is what's the base direction of each of the eyes. And then we'll work it out together. So I'll give y'all a few minutes. All right, so let's start working this one out together. Okay, we're too far temporally. So what meridian are we in? We are in the 180, right? So 180, 60 is how far away from that 180 line is 60 degrees away from the 180, right? So you either use oblique meridian or we can figure this one out with our percentages. So we're 60 degrees away, which is 75% of the sill. 75% of the sill will equal -150. Am I right? Yep, I think that's right. So -150, then we're going to add that into our sphere value. And that's going to give us -350. Is that what you guys got for your power?
Yes.
All right, so we got power at 180 is -350. And then, yes.
Yeah, I got a +50.
Yes, I was testing you. Okay, very good. Good call. That would have made a difference. All right, good. Yes, +350. Okay. The OC. Oh, you guys didn't tell me we needed a number here for too far. So you guys must have just found your base direction here. And that's okay too. We're going to put in a fake value here then. let's say it was 5 millimeters.
I thought you did
Okay.
that on purpose. too.
Oh, did you? See, I did.
Yeah.
I did. I did. I did. So, yeah, sorry. So, yeah, you didn't have anything to do your math with. So, hold on. I'll give you a second to do the math. But we could go ahead with this and figure out what our base direction was as well. So, we've got plus lenses or plus lens at that 180. So, we'll draw out our plus lens for both. Here's our nose. All right, and our optical centers are here, of course. And the OC is too far temporally, or the PD is too wide. So that means the person's eyes are going to be looking through a point kind of nasal to that optical center, and that would result in base out for both lenses. Is that what y'all got?
Yes.
Yes.
Yay. Okay. All right. So now let's do that next step and let's figure out how much prism that we had resulting here from the 5 millimeters. So we go Prentice Rule for this one. So we got 350 as the power, 5 millimeters as our error, divided by 10. And what do we come up with?
5.75.
We got 175. Is that what you guys got?
Yes.
Yes.
All right, so what that means is that each eye is experiencing 175 base out.
Yes. My question is, for test purposes, is there ever going to be a question on either classroom test or ABO where they will not give us that millimeter measurement?
There shouldn't be. There's some things that it might say that like it's on the midline or is 2 millimeters below the midline. You might hear something like that, but only because if you know what the B dimension is you can know what the midline point is because the midline is half of the B. So if I told you that, the B dimension is 40, then you could know that, well, the midline is at 20 because it's half of the B. Does that
And then
make
we would
sense?
take that, and we would take that
Yes.
20 to the Prentice Rule formula and continue everything else as normal.
Say that you're given the B dimension is 40 and the person, or let's say the OC is 3 millimeters below the midline, then you can kind of deduce what this 3 millimeters is. For this particular question, you would only use that 3 millimeters right in Prentice Rule.
Right.
Right? Because that's the error. That's how far we are from where we are. But from this information right here, you could know what this actually is because it's below the midline. Well, the midline is half the B, right? So we get 20 millimeters is our midline height, and then we're 3 millimeters below that. So the minus the 3, and we're down to 17, 20, yeah, 17. So you could find out, just trying to illustrate how other concepts, knowing other concepts like the midline could be ended up used for something. But as far as for Prentice Rule, Joni, the 3 millimeters is what you would be concerned. Like, where are we at? Where is the eye looking, or where?
Right.
Yeah.
So that
Yeah.
that part that would never be a 0, like in the question.
No, never. Let's go back to the extra credit worksheet. So transposition, that's another one. You need to do this quite often. But basically to transpose it into the opposite cylinder form. These are asking about minus. This is in plus cylinder form, so we need to change that into minus cylinder form. But basically the way you're going to do that is you're going to basically just add these two together algebraically. So again, think money. If I have -1 and I get plus 0.50, then my new sphere power is going to be what? Minus 50, right? Then I just change the sign here So I just changed that sign to minus, so minus 50. And then I changed this by 90. And
180.
so 90 would put me at 180. Put me at 0 or 180, but remember we write 180 in the prescription. So kind of the same thing here. So you just algebraically add those two together, change the sign of the minus, or change the sign of the cylinder to the exact opposite, and then change this by 90. So these transposition should come pretty quickly to you. So just, again, you can think money when you add these two together. If I've got negative $6 in the bank and then somebody gives me plus $5, how much do I got left in the bank? Minus 1, right? Then you just change that sign and then change the axis by 90, and we've got 120, right? So that kind of thing. So just practice getting used to transposing. Make sure you're real comfortable with those. You will do those on the ABO. You will do those frequently in the real world. So definitely get used to those. That's going to bring me to my first keyword. The keyword, and so write this down, is going to be formulas. Formulas. When you guys get licensed, this is how you'll do some of your continuing eds. When you do a virtual session, you'll be able to tune in from your home, but you'll just do this virtual session, and they'll give you 3 keywords as you go through this, and they put it up for 30 seconds, and you jot it down, and then after the fact you go in and you fill out a form, type those keywords in, and that's how they know that you attended and were present. And so they give you 30 seconds to do that. So now you guys will be actually kind of used to that by the time that happens. All right, this is it. Formulas is the key word here for this one. All right, so on here, optical crosses is what you should be seeing from the extra credit worksheet. I changed some of the powers so that we can kind of practice and go over them ourselves, and then that way you can still have more practice afterwards. So I changed these, just the numbers. So again, these are directly from the questions that were on the worksheet or on the test and kind of thing in the worksheet. An optical cross has a power, looking at this first one, optical cross has a power plano on the 17th meridian and 150 on the 107. How could this prescription be written? If you feel savvy enough, you can do it directly from here and without having to draw your cross, but you know, I'd recommend kind of sketching out your cross real quick. So at 17, we've got no power, and 90 degrees, we've got the plus 150. So to get this, how could this prescription be written? It could be taken off this optical cross in plus or minus cylinder form. If we want to take it off in plus cylinder form, then we want to take off the lens with the highest minus, so that we're moving, when we move to the other meridian, we are moving in a plus direction. And it would be the exact opposite for minus. So if we want to take this off in plus cylinder, we would want to start with the plano meridian first. So we would write plano, and the axis that we have in that is at 17. Because, yeah, the axis here at plano is 17. Oh, my pencil's dying. And then 90 degrees away, if we start at the plano and we head over to the 150, then we went plus 150 to get there. So plus 150. Plano is the only time that you're that the cylinder value is actually going to be the one that you see on the actual optical cross. Normally it will not be the case. If we wanted to take this off in minus cylinder form, then we would need to go the opposite direction. Basically, we would need to take the highest plus powered prescription or power. so that when we go to the second meridian that we are moving in a minus direction. So in that case, we would start with the plus 150, and that meridian would be 107, because we're right here on this one. And then we would be moving from this 150 to the plano, and so that would move it minus 150, so the prescription would be minus 150. So for this particular question, it was a multiple choice, so you would be looking for either one of these powers here. And you would select either one of those powers as your how the prescription could be written. So with this one, with the second one, which of the following represents the powers that would be found on an optical cross? So this one's basically asking you to take this prescription and write it on an optical cross. Well, we're basically doing the exact opposite of what we did. So we're going to take this axis. The axis is always associated with that sphere power. So at here's our optical cross. And at 180, we have a -3. And then to do this cylinder amount, we're going to go from the -3 up to this meridian, and we're going to increase it by -1. Let's focus in there. So we're going to go from the -3, and we're going to go -1 more. So that's going to put us at -4. And this meridian is 90 degrees away. So 90 degrees away from this would put this one at 90. So this in optical cross form would be -4 at 90 and -3 at 180. So you need to be able to do both, especially this one where you're taking a prescription and you're putting it on the optical cross. All right, so then with these, this one's kind of saying use the optical cross to write out the prescription in minus cylinder form. So I've got a prescription here that I've wrote, this +6 -6. I'll zoom in on that. So we've got +6 -6 at 45. We can tell what this other meridian is because we know that it is 90 degrees away. So 90 degrees away from 45 is going to be 135. So that's how we tell what that other one is. And this is asking us to do this in minus cylinder form. So remember, similar to this one up here, when we want to take it in minus cylinder form, we want to take the lens with the highest plus power, because when we move, and this would be the -6, because when we move from +6, I'm sorry, this would be the +6, because when we move from +6 to the -6, we want to be moving in a minus direction. So to take this, we'll take the sphere power first. So the 6, and it is associated with that 45 meridian. So we can write that axis of 45. And then we're going to go from a +6 to a -6. It's very easy to just think we moved 0, but we did not. We went from -6 all the way to 0, and then we also went another -6. Okay, so we went from -6, think money. If I had $6 in the bank, and at the end of the day, I ended up with -6, how much money did I spend? And you should say -12. So the cylinder value, and I know that's a very high prescription, but still, the -12 is the cylinder value. So how would you write this prescription in minus cylinder form? It would have been +6 -12 at 45. Can you see really quickly, if we wanted to do this, and if we wanted to have taken this off in plus cylinder form, then we would have used the -6 first. We would have pulled that off at 135, and we would have been going from a -6, and we would have been going to the +6, which would have been +12 for that one. So if we had wanted it in that, we would have taken that -6 off first, and that axis for that one was 135, and then we went +12 to get there. Okay, these questions are specifically asking you to do in minus cylinder form, so in your answer keys here, make sure you are only including that minus cylinder form. If you want to do the plus seal just for practice, you can write the plus seal down here if you want. But minus definitely is what is required for the particular worksheet. Oh, well, and basically this one's asking for you to do it in plus cylinder form. So and I use the exact same example. So for this particular one in plus cylinder form, we would need to make sure that we're going towards from the higher minus to the plus, so that we moved plus 12 in the cylinder. And that one would be 135. So this prescription right here actually is I'll just do that. So we would have minus 6 plus 12 at 135. So that's the same thing that you're doing here. And then label the cross using the prescription. Basically, we're taking this, a prescription that we're given, and then we're going to put it on the cross. So doing this one on the cross, here's my cross. We'll say that this is 150. And remember that this power is associated with that sphere, so we got minus 10. And then for my cylinder value, I'm going to go from minus 10 and I'm going to plus 3 into that. So think money, negative 10 in debt. I get $3. That leaves me with minus $7 in debt, right? And then my axis here, 90 degrees away, should be 60.
Yes.
All right, would be 60. Nominal power formula, that's the other one. There might have been some mistakes from this one, because remember, nominal power formula is just what's the power of the lens looking at the front plus the back equals the power. So the front of the lens plus the back of the lens equals the power of the lens. This is kind of the base level of that. On all of these, you're asked for the back curves. Even that one, you're asked for the back curve. But then it switches it up and asks for the front base or the lens power. As long as you're given two of these variables in this formula, you can solve for any of the missing ones. These are so common in the lab, especially because this is the one that the lab is most concerned with. They're given a front surface curve, and then they're given what the power of the glasses are. So basically, this is the base curve of the lens, and this is the prescription that we have. And then what the lab wants to know is what back curve do we draw, do we write on here, or do we cut on here to create this RX power using this particular base curve. So when it's just the front plus the back equals the power, that would be like this one down here. So what's the lens power? We're told that the front of the curve is plus 10, and the back of the lens power, and the lens power. Ugh, that should not say on the lens power. That should say the back of the lens. The front, and then this should be the back. The back can't be plus, it would have to be minus. And the back, well, let's say the back surface is 5. Yeah, let's do it that way, because that's how it should be, not the power of the lens, because this is asking us for the power. All right, so this one is the front, basically, plus the back equals the power. So plus 10 plus that minus 5, minus 5 is going to end up with a power of a lens of plus 5. Right? So this one's straightforward, but in any of these other ones where you're either asked for the back curve or the front curve, you kind of need to change this formula around, and it will always be the power minus what you have will give you what you want. All right, so like this one right here, we're given a front surface curve of plus 6, so there's plus 6. Plus what curve equals the power of the lens, which is minus 10. So you can either look at it like this and just kind of subtract the 6 on each side, and then you know that we got a minus 7 here. Or you could say, doing it this way, then the power of the lens is minus 1 minus whatever I have, which I have the 6 diopter curve, is going to tell me I need whatever I want. So this would be the RX power. This would be the front base curve, and this would be the back surface. Does that make sense? So these are just a matter of making sure that you're either, that you're solving for whichever variable, however, whatever variable you need to just pay attention to, whether you're being asked to find the back curve or the front curve or the lens power, and remember that that front plus back equals the power, and you should be able to kind of work your way out of that one, or you know what I mean, work your way through that one. Speed of light, that was another one that had some issues. The main thing is that the speed of light in the vacuum, this 186,000 miles per second, is always on the top of the formula. So it's always going to be 186,000 miles divided by something is going to give us what we want. Okay, so if you're given, whether you're given the miles or whether you're given the index, you just plug that into where the question mark is, and it'll give you whatever you're being asked for, whether it's the index, whether it's the speed, whether depending on what you're being asked. So looking at this one, we would just 186,000 divided by 106.9. There we go. And then we would multiply those two, and then that would give us an index of the material, right? And then the same thing with ones where you're using the index of the material. And no, we don't have any lenses that are diamonds, but I think a diamond is pretty interesting how it moves in there. Anyway, so you just take the same thing, you take the 186,000 and you divide it by the index that you have, and that will give you the speed that you're looking for. Basically, these two variables down here can be switched around. Whether you want the index or whether you have the index, it will tell you the missing information. All right, boxing system. This is just one that you have to just kind of get in there and memorize. You should be able to label all of these. What is this measurement here? What is this measurement, up and down? That kind of thing. I do want to point out that the DBL stands for the distance between lenses, right? And so we're not measuring down here where the bridge might be. That would be too wide. That is not equal to the distance between the lenses. You would want always to go, let me change this to a brighter color, always to go from the narrowest point between those two, and that's the distance between the lenses. Can you see how this would not be the narrowest point between those two lenses? So this is wrong, this is right. So make sure you're, don't fall for what is a common thing in the industry, is to measure that amount where the bridge actually is. You're actually looking for the distance between the lenses for that. Another one that I want to point out is the ED. The ED measurement is oftentimes pictured like this, and people get the impression that it is a horizontal measurement. It is not. The ED is a specific measurement, and it's equal to a circle that will basically enclose the opening of the glasses or the opening of the lens. That circle is an actual lens. You guys have been dealing with those finished lenses in class. That diameter, what we need to make sure is that diameter will still make cut out when it's used. So to do that, to find a circle that will cover this entire opening, we go from the very center of this, which is the boxing center, right? So that 4 is your boxing center, right? So we go from there and we measure to the farthest point in the lens opening. That could be from here to here. It could be from here to here. It could be from here to here. It could be anywhere, just as long as it's the furthest point from the boxing center. Because what we're ultimately going to do is have, and I swear I probably won't be able to draw a very good circle, but a circle that kind of encloses this opening. So we basically have a circle that from this boxing center to that opening, that is our radius, right? And so this from the boxing center to the furthest point is the radius, and the radius is or the ED is 2 times the longest radius. And students usually memorize this and they're like, oh yeah, I can find that on a test like nobody's business. I dare you to ask me that question. But they don't necessarily understand what that means. And so this is the radius that we're looking at here. This from the boxing center to the furthest point in the opening. And then we take that radius and we multiply it by 2 to give us our ED. So that's what that means. So it means this radius times 2 equals our ED, right? So if this radius here I measured was, let's say 30 millimeters, what would be my ED? We just take the 30 exactly times 2, we just double it, and so my ED would actually be 60. All right, so hopefully you guys understand a little bit more about the radius and why, because the radius comes in really, it is very important, and the ED is very important when we're dealing with lenses and making sure that that diameter of the lens we choose is going to make cutout, is going to be large enough to cover this entire lens opening once we have decentered it and placed it into the frame and edge it. Once we cut the excess material off of the lens, the blank, that it will all fit into the frame. Another one that I want to point out is the boxing center. The boxing center is here to here, right? So that's our boxing center distance, is this point right here. Also, we'll call this like the frame PD, right? Because this is from our boxing center to our boxing center. This measurement here is also, in practice, it's really hard to find where the boxing center is of your frame in a time limit that you actually have. So there's an easier way to do it, which is measuring the A dimension plus the DBL, right? So A plus the DBL is also equal to our frame PD. You might have heard that already, right? So if I have a 50 for the A and a 20 for the DBL, then my frame PD is 70. Well, that is also equal to the distance between the boxing centers of this pair of glasses. This is why we care about this measurement, is because of where it is. Because the next step with this is that we have a person's eye in this pair of glasses. And what we need to do is make sure that anything that the optical centers of the lens get moved from where they begin their journey to where they need to end up at. So we need to know what this distance is here so that we can move the optical center over to that patient's eye. And if we know what the measurement is from here and the patient measurement from here, then we can figure that out, how far we need to move. So that's going to lead us into decentration. But anyway, what you need to know for now is that your frame PD is equal to the distance between the boxing centers, and that measurement can be found by measuring the A plus the DBL. When you're doing it on tests and in paper and everything, you take the A measurement and the DBL and you add those together. When you're using a real ruler, you need to be measuring from the outside of the box and you measure all the way in to here as one measurement. And what you'll know, or or find out is that that is going to be equal to the boxing center distance. I'm going to show you right here. All right, so there's, if I take this measurement, this equals that. See that? So there is the A plus the dBl, and that equals this measurement right here, so that we can trust that measurement. Because otherwise you have to sit and find where half of this is and half of this is in order to find that boxing system, or that center. So that's what these questions are. And then these questions down here, this is just asking you some familiarity, some things like that. The Abbe value here, we've got, you see your ranges here. These are kind of the Abbe value to kind of the lowest Abbe value. Knowing that polycarbonate is considered the lowest Abbe value is definitely something that you want to know for the ABO. And that crown glass, even Trivex, that these all have actually the CR39 and the crown glass are the ones with the highest Abbe value, which means that they have the least amount of aberrations. If you'll remember, aberration was, remember dispersion, when the white light comes through a prism and it's broken down into its component colors, right? And remember that light comes through and then it's broken down as component colors and it comes out as like a rainbow on the other side. That was dispersion. And dispersion is how much this breaking of white light happens. Because what ends up happening is in the eyeball, remember that whole, we want everything to land right on the, we want it to land right on the cornea or the retina right here. But if we have light rays coming through that are all broken up into their component colors, red, green, and blue, then you get a little red image, you get a little green image, and you get a little blue image. And all of those, only one of them can really land here. So you would have a little red, a little blue, and a little green image, and they would all be, only one of them would be on the retina. And so this is how this dispersion kind of ends up causing these kind of rainbow effect in there. And that rainbow effect or that dispersion is calculated as an Abbe value. Closer to 60, less chromatic aberration. Closer to 30, more chromatic aberration. So these last two questions are I just want you to understand the concept between what happens when the higher the Abbe value, the blank in the lens. The lower the Abbe value, the less the lens. That you can all find in this material right here. Okay, all right, and so now for this other part of it, there was the lensometry readings. So this is the second extra credit worksheet that's there. And what we've got is you see the power drum right here, and then this is where it's actually focused on, and it tells you right here the amount. And if you look, these are the three skinny lines, right? And so those are the sphere lines. So the sphere line is focused. And then when we have our second reading, we've moved to plus 50, and you see that our cylinder lines are focused. You see the three thick lines are focused. Notice that they both cross at the very center of the target without being moved, right there. So they both center at the target. And then we look down and we see that the axis wheel is set for 0. So the axis wheel reads 0. I did write in that we write that in the prescription as 180. And so then we would take and we would write this from these power readings. So when we give our first reading is our minus 65. sorry, minus 62, minus 0.62. And our axis wheel is at 180. So we write our prescription in here with the minus 62. Axis is at 180. And then when we look at our cylinder value, we went to a plus 50. So we went from minus 62 to a plus 50. How far did we go? And when you're using a real lensometer, you'll be able to literally, you can kind of count how far you have gone on here. But questions like on essays and things like that, or tests, you can always take this value and subtract that one. So if you put it in your calculator, the second number minus the first number should always work out for you. So if you put that in your calculator, we've got plus 0.50. So we got 0.50, and we're going to subtract the that first reading, and make sure you put in your minus signs there, because basically you're going to end up adding those. And so I get a plus 112, which this is my actual cylinder value. And then it asks you to transpose that. Here's another point that I want to make. Notice that the sphere and the axis in each of these transposed prescriptions are equal to the power drum readings and the powers located on the optical cross. I've tried to point it out here that this axis and the sphere power, right? So we can read this as minus 62 at axis 180. And we can also read at axis 90 that we have the plus 50. Notice that those are the two powers that I have in my readings. That these two powers of the plus and minus cylinder form are equal to the sphere readings for these two. And that these are also, and I wrote them over here, 62 at 180 and plus 50 at 90. If we plop those onto an optical cross, they're the same on the optical cross. So that 62 at 180, here's that, the 180, the minus 62. And then the plus 50 and the 90. So there's our 90, and we got plus 50. And yeah, and you can see that depending on which way we go, we have our cylinder value right here. So I just wanted to make the distinction, or the connection, if you will, between the transposed prescriptions, the powers in the two major meridians, and the powers on the optical cross. That they're just several different ways to kind of double check yourself. So on this one, we'll work this first one out together. I haven't changed this one. So my first reading is minus 7, and my second reading is minus 4, and my axis is set on 12. So the prescription, this is my sphere power, cylinder power, and this is my axis. All right, so just like we did up top here, I can take my sphere value reading at face value. So my sphere is going to literally be what I've got here, and along with my axis. So these two are going to go together. So I can start writing my prescription is minus 7, and the cylinder axis is going to be 12. And now I just ask myself, how far did I go from minus 7 to a minus 4? Again, you can think money with this. If I had negative 7, or I was in debt by $7, and at the end of the day I was in debt by $4, then we can see that I gained $3, right? The other way you can do this is plug this directly into your calculator. But yeah, the biggest thing is make sure you keep up with the signs, because you're subtracting. So you take that second reading, and then you subtract the first reading.
And for the transpose part, if the answer is like a minus seal and it says transpose, we're obviously transposing that to a plus seal.
Exactly.
Okay.
Yeah, because some of these are going to be like this first one was in plus cylinder, so you would transpose it to minus cylinder. This one right here, we're moving from a -2 to a -3, so that one's going to be a minus cylinder, so this one would then be plus. Yes. But so Kareem has you guys doing, I believe you guys are down here in optical measurements. Don't even mess with these yet. Just you'll learn those. I mean, you can go in if you're real nosy, but you don't really need to. This one for definitely for Kareem's class, but this little simulator here for lensometer, again, we've got two more semesters to work with this. But this is one of the tests you'll be doing, and this little simulation goes through all the details, but it has a little lensometer on here, and at certain points in the in here, you'll be able to move different parts of these around. So like the axis wheel here, you'll be able to move around the power drum wheel. Let me get to those. And yeah, and it'll show you the target on here, and it's very, very, very similar to the kind of the basics that you're learning about the lensometer. So it's a good source to come in here and kind of get the basics down, especially if you don't have any experience with the lensometer. And it actually lets you start to run it yourself. Yeah, so it'll have like simulation is active so that you can start moving the power drum and seeing what happens. So you see, as we move that power drum further and further away from where we need to be, we lose complete focus. And then as we start getting closer and closer to the power that we're actually measuring, we start to gain focus. And then when we go past it, again, we lose focus. So you can use this to kind of practice around with it. And then this axis wheel up here allows you to move that axis. And this simulation is a tad bit easier than using the real lensometer. For the test, it's going to be great. Regardless, though, you will still need to be able to use the lensometer confidently. And I'm going to teach you how to do that. But this simulation will give you some basic understanding of, looking for your sphere power, getting used to that, the sphere and the cylinder, and finding those powers on here. It does get into some of the prism and other things like that, and so I would stay away from those for now, but there's certain slides on here that you could use, and this like says verification, so where we have the left lens in here, it kind of tells you that, but you can see that the left lens, this is the right lens, it's away from us. Remember, they're always facing us. So we've got the left lens in here, and we can kind of start to move the power wheel around to start to focus. And remember, we want our sphere lines to focus first, so these three thin ones, and we're just going to slowly bring that in until, did you see the difference? I often, when I'm using this, I don't look at these so much as I look out here at the clarity of these lines out here. So keep your eyes out here as I'm going to rotate off power. See how they blur out? And now I'm going to rotate back towards power. You'll see it all of a sudden it clicks in and it's real bright, right? So that's too much plus, perfect, and too much minus. So and you get right there and you get your sphere lines in place. And then when you're looking, so this would be our first reading. So left lens, we got a +2, and we look over here at this +2. And so we say, okay, so that looks good. And our axis is at 90. Our axis right here is at 90. So that looks good. And then we want to -1 more from here. So if we're at +2 and we want to -1 more, we're heading in a minus direction. And that's going to leave us at +1. So we're head on down. And we go to -1. Ooh, right there. And you see how the cylinder lines now are in sharpest focus. All right, and so we didn't write, even though we're at +1 on the dial, we're not writing +1 because this cylinder power is equivalent to both of these, basically +2 -1. That's why we're at the +1. So there's another one that they give you the option to. I have that happen on my computer a lot. I don't hear the volume of these, and I've found that if I just click on this little yellow slider down here, once I click on that, then I can hear the person talking over the simulation, so that I can, yeah, so that you can hear it. But then, yeah, so the simulation is active. So you can see here, this is like a spherical pair, and everything focuses all at once. You see our sphere lines are focused and our cylinder lines are in sharp focus, and we're right at 250, right? Because here's 2, there's 3. We're in the plus side, so we're at plus 250. This is a left lens that's in there. Remember, they're looking at us. So plus 250. So that kind of lets us know that we're in the right place. And then this one will have you do the same thing. Yeah, so you look in here and you just move the power drum and into sharpest focus, and then you can take the measurement. See how everything, all of it is all in focus. We got sharp lines out here, sharp lines here, and then this is all correct. There's some other ones too. Go back to my notes. Yeah, and then so then we've got like a cylinder value. So this one shows us cylinder and what we're seeing in there. And again, we're going to be moving the axis, and then this is also, we're going to compare what we've got here to what we've got in the prescription. So again, we're looking at the left eye, and you go, well, the simulation's not active, so let's go to the second one. All right, so now here, yeah, okay, here we go. All right, so here's our simulation. So so you can see that these are elongated in a way. So this lets us know that we're off axis. All right, this lets us know we're off power. First thing I would do is kind of blur everything out, right, in the high plus, because most everything needs to be in minus cylinder form. So we start to rotate just before we start to get everything in focus. Now we're going to fix this axis. So we start to rotate that axis until we get straight lines, all unbroken and straight. We're still not as clear as we want, so we're going to keep moving in a minus direction. So keep rotating until, boom, right there. These come real crisp in focus. And then what power do we have? We're in the plus section. We're between +3 and +4. And this is right here at +325. We check our prescription. We got +325 here. Our axis is supposed to be 45. This seems straight to me. And our axis is at 45. So we're perfect on that. And now let's find out if we've got a -150 cylinder. So we're going to go from this 325 where we're at on the drum, and we're going to go minus. So we're going to be moving in this direction. We're going to -150. If we're at 325, 1 diopter if we go right to 225, that's 1 diopter, right? And then we're going to go another -50. So that's how I use the drum to count. So we're at 225, we go another 50, and that puts us at +175. Everybody see how I did that? So basically I went from that plus, instead of doing it you could do it in your calculator, but you could also kind of count it right out on the drum. So we're at -3, we're at +325, and we go -1 from that. Would take us to 225, and then we go the next -50 from there. There's a quarter, there's another quarter, so that's minus right there. Okay, and we see sharp focus here. So this prescription should be right, and it is. You should have found that the power and the axis match exactly. So then there's a couple of other ones on 14, 18, 21. So this one has you practice neutralizing it. So this would be where you don't necessarily know what the prescription is, and you're going to move everything around and try to get your axis set right, try to get your sphere and your cylinder powers right so that you can put in your answer. Now with these, you don't have a prescription you're necessarily checking, so you just kind of write down, so simulation is active. So what I would do is blur everything out in a plus direction, right? So I just make everything blurry in a plus direction and start to rotate slowly in a minus direction. You'll start to see things focus. So we're starting to get an image here, but I don't want to go too far because I also know since these are kind of off, kind of at an angle, I want to rotate my axis to get my sphere lines in focus. So I'll rotate that and then see my sphere lines are starting to come into focus. They're not perfectly focused. You can see that out here. These are blurry. So now we're going to rotate the power drum more minus until we get that to come into focus. Perfect. So now you see this real bright in the sphere lines. So I would be reading a -2 for my sphere. So you would jot down, right? You would say, okay, -2 is my sphere power. And I already know my axis is 60. So 60 for my axis. And now I'm going to continue to rotate until my cylinder lines come into focus. So again, in more minus, head on minus, and we're looking for those cylinder lines to come into focus. Boom. Those come into a bright, crisp focus, and my power drum is at -3. So I was at -2 and then ended up at -3. My cylinder value in the prescription should be -1. So does everybody see that? So we should have -2 for the sphere. And then I go from -2 to -3. I went -1. So the cylinder value in the prescription should be -1. And the axis would be 60. All right. So this is kind of a fun thing to, or I don't know about fun. I think it's kind of fun. A fun thing to kind of practice around with the simulation. There's another one on 18, and you just get to type, you just kind of write down what you get, and you get to practice you moving that around and finding that. You're going to do this in class again next week when we do. This kind of just talks a little bit about applying the standards. You will need to be doing that, and we are starting to work on that in class. They do give you the standards here. This kind of lets you know that they'll give you the standards when it comes to this exam, the practical exams. They just kind of looking to see that you can apply that. And so if you're really curious, you can get in here and kind of see, on the test, they have a little test for you or whatnot. I would be careful getting into any of this just yet, but I think 27, I'm going to rush over to that one real quick. 27 is where you'll start to measure, and you may be familiar a little bit with this one with in Kareem's class, because it has you pick up the PD ruler and you move this around and you do your measurements and then you compare them to what you get. So this kind of just gives you, the next step that we're going to be doing, of course, and we have been in class, is actually taking these measurements, a monocular PD and the binocular PD. And they also do another one for the seg height in 29. So this one, they have you take that and you can measure here. One thing that they do on the simulation that does not exist in the real world is this little white dotted line. And they talk about that in this when they're going over that. But this little white dotted line, basically that's telling you where the lens ends. So yay, right? So you don't have, in real life, we don't have a little line that tells us that. We know that, we have to assume that from the bevel inside the frame is generally about 1/2 of a millimeter. So we usually just measure to the bottom of this rim where we can see the lens, like that demarcation area. And then we just add a 0.5 millimeter for this particular test. When you're doing this one, you'll be measuring from the, kind of the top of that seg height, and you'll measure down to where this white line is. So you can see, everybody, it might be small, but can you see that? I can't zoom in. You can see, are you guys getting a 12 for the seg height on this one? So we see there's our 10, and then we're 2 down from that, so we're 12, and we can double check our seg height here with the 12. Yeah, and then the next to this goes into add powers and progressives and things like that, so you don't need to deal with that just yet. But the main thing I wanted to let you know is that if you want to, you can get on this simulation and kind of practice around if it will help you. The way you can get to that will be to go to the ABO-NCLE website, ABO-NCLE. Let me do it like it's not already saved. NCLE, ABO-NCLE home. So you go to the home, and then up here in the exams area, you can come on down to the practical exams. And then that's where you'll get to the tutorial. So you can go right into the tutorial and practice any one of those, either the lensometer, they even have some little practice questions, but the lensometer, and then probably for Kareem's class, you're messing around with those optical measurements.
Miss Tracy, did you provide the other 2 words for the session?
I did not. Thank you. I see that was a test. So the other 2 words are cylinder, SYLINDER, and then the last word is Z80, Z and 80, as in ANSY's Z80 optical power tolerances. I am going to put those up here on the screen for a second too. We got cylinder is the second keyword. And then the third keyword is Z80. And I did on that first keyword, remember I accidentally put an S up there. I went ahead and added the S in. So whether you put it in without an S or with an S on that word, you're good to go.
I have a question. On the extra credit worksheet, theory and formulas, on the nominal power formula part, the very last question, number 5, is the second number supposed to be a power or a...
That was for this one. It should be a back surface. So yeah, so I would scratch out the power of the lens and change that to the back surface.
My question goes back to right after we started, we were on Oblique Meridian, and then we went down to doing the Prism. There was one that you were showing on the worksheet. That was, I think it was the very first one that we did, and it said higher than requested. And for some reason, I was thinking if it was higher than requested, they would be looking up, not down, but the correct answer was down. And I was just having trouble understanding that.
It's the OC.
Yeah. Yeah, because I think the key here is that the OC is accidentally placed 5 millimeters higher. So that's where I was saying that, find the OC and then, like where is the OC versus where is the eye? And if the OC is placed 5 millimeters higher, then that means that the person's eye would be looking through below the OC. Does that make sense?
I think so. I think I just was overthinking it.
It's okay. I was just asking if it's the eye, it'll say the eye, not the OC. If it says the eye is looking above, then we know it's above the OC.
Yes. So no matter how it's presented to you, if you can locate where the optical center is and where the eye is, then you've got what you need figure out that base direction. Yeah, that's kind of why, like down here in the base direction part, whether the lens, what's the power are we dealing with, whether it's plus or minus, and what that meridian is. Are we in the 90? Are we in the 180? And then know where your optical center is and where the eye is. And that will work every time, no matter what the particular situation. Just don't assume. Make sure you go back to the material that you're given and say, okay, well, where is what is happening on this lens? Where's the optical center? Where's the eye? And that should always work out for you then.
The minus cylinder, we always take the highest plus.
Yes. And you have to take that one like the highest plus, even if there's two minus lens powers there, one of them is a higher plus power. One of them, AKA, has less minus.
Right. It'll be like, yeah, the lower minus of the two.
Yeah.
Okay.
Yeah.
That's the one that I use for writing the prescription.
For optical crosses.
Yeah. Like
that one is taking the actual cross that you have, one of these two, taking the power that you have on the cross and deciding which one that you'll take first. And if this one is asking us for minus cylinder form, so we want to make sure that the first one that we take off is always going to be the
plus.
The highest plus.
Okay.
And so looking at these two powers here, which one is the highest plus?
-1.
There you go. And you can just kind of go right down the line and do that with all of these. Which one has the highest plus? That's the one. That way you make sure you're always headed in a minus direction. And then with the plus, excuse me, with plus cylinder, it's going to be the exact opposite, or you are looking for whatever has the highest minus power.
Okay.
So again, you look right at those and which one is the highest minus. Same thing with this one.
Okay.
Yeah. And then which one of these is the highest minus. Even though they're both plus, one has more minus than the other if you look at it like that.
The +1.
Correct. Well, yeah, +1, because we want to be moving in a plus direction. So yeah, +1, and then we move up to the +350. So yes, that would be the direction. And then the same thing with this.
On the worksheet that we just did last night, one of the questions I think I missed said that when we're measuring the segment height, I start at where the segment, my dot is on the glasses that I make for the person, and measure down. And on the simulation that you showed us a little while ago, they did the same thing. But I think it was wrong on my quiz when I was taking it. And I just wanted to know, do you have to do it one way or the other?
Yeah, the question says, which of the following describes the seg height measurement? And it says the vertical distance from the lowest part of the lens bevel to the top of the seg. Oh, so if you're asking whether you can measure where the 0 can be at the bottom or at the line of the seg, that I don't think that matters. Because the other ones are horizontal distances. Those are horizontal measurements, so we know that one wouldn't be the case. And then the other possible, so the two answers are the vertical distances, right? And so one answer says the vertical distance from the top of the segment to the lowest part of the lens bevel directly below the center of the seg. And then the other one says the vertical distance from the lowest part of the lens bevel to the top of the segment. All right, I see your confusion on that one. The correct answer is the vertical distance from the lowest part of the lens bevel to the top of the seg. Not because you're going from the lowest part to the top of the seg, because it could also be said from the top of the seg to the lowest part of the lens. The key here is that the other option talks about that same measurement, but doing it directly below the center of the seg. All right, there. We'll pretend like it's a really aviator shaped pair, okay? because this is the classic one that this actually often happens with. When we're measuring the seg height, we want to measure from the top of the seg, which I think everybody agrees with is relatively easy to remember, but we want to go to the lowest point in the frame. So just like as if we had boxed this pair of glasses, right? We want to make sure that when we take the measurement that we're measuring from the top part of the seg, so this whole line here, down to the furthest point. The first option that some people do is they'll measure that. They'll measure directly down the center of the seg, and then let's say they got something like 20, right? So they say, oh, I measured my seg height and it's at 20 right here. Well, the real true way you're supposed to measure is to make sure that you go from the top of the segment, yes, but to the furthest point in the frame, the lowest point in the frame. So we're actually measuring out here, and let's say that that is 25 millimeters, right? So 25 millimeters is the real height because we're going from here to the bottom of the box. So we're actually measuring this distance. A lot of people will measure right below where the center of the seg is, and this is actually just incorrect. You'll end up getting a seg height that's too low, because the lab is going to take this, and if you ordered a 20 seg height, they're going to put it at 20, and so what that would end up looking like is you'd end up having a seg that's further down like this. It would actually be 5 millimeters lower than it's supposed to be if we wanted it really at 25, which is up here at this point.
The 8.2 worksheet,
Mm-hmm.
kind of silly, but it didn't give me my full points because I wrote, the question was, in relation to nominal power formula, what do the following variables represent? It says F1, F2, and Ft. So I put front curve, back curve, and the nominal power. And it took points away because I wrote the word curve.
Oh, that's fine. I just didn't in there. You'll get the points for that. You could have said front curve, front power. Any of those would have been okay.
Okay. Is the speed of light index stuff, the speed of light divided by and all that, is it really that simple?
Yes.
So all I had to do was take, if it's asking for the miles per second, the 186,000 divided by the 2 point whatever. And that's
Yeah.
it.
Yeah. You either, yeah, 186,000 divided by what you have gives you what you want.
Okay.
If anything, rounding, some students are like, I don't know how to round these or what I should do to round these, but I'm usually pretty flexible with that as long as I think that you did the math right. Then all the questions on the ABO are all going to be multiple choice, and I think given a multiple choice question, if you've done the math correctly, that they won't have something up there that is dependent on whether you rounded correctly or not.
Speaking of rounding up, so like on that part of the speed of light, the last three, do we have to write the point blah blah blah, or just leave it at the 1,000? For number 3, I got 76,859 dot blah 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 blah, but I just left off the dot blah blah blah.
That's perfectly fine. That's perfectly fine. You don't need the dot blah blah blah.
Okay.
You'll notice on the ABO they give you a lot of prettier numbers.
Okay.
Because they'll give you'll see a lot of 1 seals, 2 seals, 4 seals, stuff that you can work with easy, and axes at the stuff like that. And a 10 millimeter anything with an error of 10 millimeters is always nice, because if you're doing Prentice Rule, something is like 10 millimeters down to read, right? That one's a beautiful one, because let's say we've got a 4 power and they look 10 millimeters down to read without even doing the math. I can tell you right now they're going to experience 4 diopters of base down prism. And how do I know that? Well, if you put this in Prentice Rule, right? Big D times little d divided by 10. You plug that in. I got 4 times 10 divided by 10. These just cancel out, and it leaves me with 4, right?
Yeah.
So I was quickly able to find that, and then I've been doing it so long, I just know that somebody minus lens, they look down, they're going to experience base down prism.
Right.
Yeah, so any kind of times where you get a 10 is just a beautiful thing. A 5 is kind of the same way. It's just going to be half of whatever that power ends up being if it was 5 millimeters, I believe, right? Right. Let me run one real quick before I lie to y'all.
20, so it should be half.
So it should be 2. Yeah, half, right? 20, yeah. And then divided by 10, yeah, 2. So yeah, things like that, little shortcuts and stuff. Believe it or not, I know you guys are probably more familiar now with doing the oblique meridian formula, but you will find that you actually don't need to use that formula that much on the ABO exam because they will have those axes that are in that meet that little 30, 45, 60 rule.
Okay. Well, it's kind of not nice. After all this practice, they should put some in there.
Well, yeah. Now, if you ever wanted to get, like, you guys are technically, when you get done with the program, you are like thoroughly trained to the point where you guys could go ahead and take your advanced ABO and pass that easily. That's after at the end of the program. Once you've gone through everything, you'll be so kind of versed in the formulas and stuff. And on that one, yes, they have you use that oblique meridian formula a lot more. And not saying that you can't use it on the ABO, because you can if you're fast. Some people are just as fast at doing that, and you can double check yourself, yeah. But any kind of shortcuts that you can find, are also helpful. And we end up doing that one more in practice because you can't really, if somebody comes in with a crazy prescription and you're like, okay, I have no idea what does this one look like. So let's say somebody comes in, I have a friend, he's got a -6 +4 at axis 30. Then, you might want to be like, oh, okay, well, what powers am I really looking at 90 and 180? Not because there's an error in the prescription, but because before I sell this person a pair of glasses, I need to know, or how much power do we have in any given meridian? Like, where is my thickness? So that's when it comes important, and you're like, okay, well, 30 degrees, 30 is 30 degrees away from 180. So I've got 25% of this, which would end up being a +1. So I'd really be looking at -5 here. And then 60 degrees, 75%. So I'm really looking at so 60 degrees for the 30, we're 60 degrees. So 60 degrees is 75%. So 75% of the 4 times the 75% is 3.
3, yeah.
Plus 3 into that. So we should have a -3 here. Yeah. So just things like that. And not, and in real life, because then you would know, okay, well, I do have a pretty good amount of power here on the 180, and it's gonna, I want to be careful of getting a frame that's too big and wide, so maybe not so much as a problem for their clear pair, but maybe when they go looking at that sunglass pair that they really want that oversized look, that I consider, okay, I got a -5 in that meridian out there on that 180, and that's going to end up being really thick. And so just so that you're aware that you're going to have a lot more thickness in this pair than you will that one because of the way it's shaped and how big it is. That kind of thing, just to help quell issues before they happen. Y'all have a good day and enjoy your break.